Okay, so with this video, we're going to discuss a way of tackling a conjecture of TxGraffiti that first appeared in 2017. This conjecture states that if G is not a complete graph on 4 vertices and it's cubic, then the zero forcing number of the graph is at most the independence number of the graph plus 1. So over the past week, I've developed an algorithm that generates a zero forcing set that's equal to an independent set plus 1 in all cubic graphs that are not Q4. So let's just do a few examples of this algorithm. Algorithm. Okay, so let's start with maybe one of the most famous cubic graphs, maybe the Peterson graph. So let's draw the Peterson graph. So here's the Peterson graph. Okay. Okay, so we are going to first find a maximum induced tree in this graph that also maximizes the number of degree 3 vertices. So let's find one. And then here, and down here. Okay. Now, if we add any vertex to this tree, we're going to get a cycle. So we can't do anything more. What's more, all of the vertices outside of this tree belong to an induced path on at most 2 vertices. And we can argue that in another video, but that's the case. That you find a maximum induced tree, and you can't find any other maximum induced trees that aren't P2s or P1s, then you're done. So that's the goal, really. So this one tree here, the biggest tree, we're going to call T1. Okay, and we're going to note that the maximum degree of T1 is equal to the maximum degree of the forest F, where the forest F consists of these trees. And this is a spanning forest of the graph. So once we do that, once we find our largest trees, our trees of maximum degree in this forest, we can then color the leaves of this largest induced tree. Okay. In the general algorithm, if the max degree of a component is equal to the max degree of the forest, then we're going to color all the leaves of those components. And we're assured that this is going to be an independent set. So the way that this is going to work is now we're going to let those leaves also be in an independent set of the graph. Okay. So we have a set of blue colored vertices and a set of independent vertices that are currently the same. So now we're going to add one more blue colored vertex and get the zero forcing process started in this graph. So how do we do this? Well, if we have an isolated vertex outside of a maximum degree tree, then we're going to color that. But we see that here, this maximum degree tree here is only adjacent with P2s. There are no isolated vertices, so we can't do that. But we notice that this P2 here has a leaf that's adjacent with 2 leaves of the big tree, which are colored blue. So what we're going to do is we're going to color that vertex blue, and this is going to give us a +1. Okay. Now, because this had two leaf-colored neighbors in a big tree, a maximum degree tree, it will be able to force along the P2. And we're going to continue the zero forcing process until no further color changes are possible. Well, no further color changes are possible. Every colored vertex either has all of their neighbors colored or two non-colored neighbors. So what do? Well, we know that we stopped here in the case that it's adjacent with two leaves. Okay, so what we can do is we can uncolor one of those leaves and then color a neighbor of that in one of the components here. Now this is allowed to force up. And once that force is there, this is a blue colored neighbor. So now the forcing process continues. And there. So the set of blue colored neighbors that we augmented from to get to is a zero forcing set. And the set of these circle vertices here, that's a zero forcing set. Right? No, an independent set. So if S is the set of blue colored vertices, then the cardinality of S is equal to the cardinality of the independent set, which I denote by I, plus 1, where the plus 1 comes from initializing the zero forcing process. So let's look at another example. Maybe the hypercube. That's another famous graph. Okay, so we'll draw the hypercube. Okay, so let's find a largest induced tree that maximizes the number of degree 3 vertices. So maybe right there, right there, right there, right there. Now, if I add any vertex in this graph to this tree, I get a cycle. And then here's another component there, and then there's a component there. So there's only one largest tree with maximum degree equal to 2 in this case. So this will be our T1. Okay, this big tree, right? And then again, maximum degree of T1 is equal to the maximum degree of the forest. So we do the same trick. We observe that the leaves of this maximum degree tree are independent, and we color those. Those are colored blue. We also know that those are independent. Keeps on falling. So we know that they're independent from each other. Okay. So what can we do now? Well, if there's an isolated vertex adjacent with two leaves, we color that one right there. Now, because it was adjacent with two leaves, we know that it will force if it has one uncolored neighbor. But we're stuck now. After that vertex force is there, we're stuck. But why are we stuck? We're stuck because we're not adjacent with any leaves. So we know that this vertex must be independent from the original vertices. So we can include that in our independent set and then color just some neighbor of it. Now, after we color that neighbor, then that vertex can force. Okay? And then we just allow the zero forcing process to keep on going. So here we have a zero forcing set with cardinality 4 And we have an independent set with cardinality 3. So again, we satisfy this property. Okay. But now maybe let's look at an example where there's more than just one biggest tree. Okay. So one such example looks like this. Okay, so here is another cubic graph, and let's find a biggest tree that maximizes the number of degree 3 vertices. Okay, now if we add any vertex to this tree, we get a cycle. And among all possible induced trees, this is one in the original graph G that's on the largest number of vertices. So we're going to call this one T1. Now, we have this other component here. Well, in this component, we're going to do the same thing. We're going to find a largest induced tree of this component that maximizes the number of degree 3 vertices. And then if we add any vertex to this tree, we get a cycle. Okay. Now, an important property of doing this process is that at T1, the leaves were only adjacent with P2s or isolated vertices. And I'm going to call this one T2, by the way. Now, T2 has at least one vertex with 2 neighbors in T1, which is not too hard to argue. And then all the leaves of outside of that one that's adjacent with T1, all those leaves are also adjacent with either P2s or P1s. So here is our forest decomposition of the graph. Okay, so so the max degree of the forest F is equal to 3. And I'll call all the vertices that aren't subtrees with max degree 3, I'll call the collection of those together G2. So then F is equal to T1 union T2 union G2. And G2 is the collection of all these P2s. Okay. So as before, we're going to color all the leaves of components with max degree equal to the max degree of the forest. So we're going to color these. And observe that those leaves are necessarily independent from each other. So we can include those in some independent set. Okay, so this is a part of our initialization phase. So now we just need to get the zero forcing process started. Well, what we're going to do is we're going to choose the force T1 to become all colored blue first. If there are any isolated vertices adjacent to T1 that were in G2, then we would color that one of those to get the process started. Since there's not, there's only paths. We just choose one of the paths to get colored. So I'll color this one. And that's where we get our +1 from. So now we let the zero forcing process start. and we're stuck. And in this case here, we're stuck because we're not adjacent with any leaves in P1. So what we can do is that must necessarily be independent from those prior leaves, and then just color one neighbor of it. So there's a one-to-one correspondence. When we gradally color something, it corresponds with a vertex that we added to the independent set. So then this can force here, and just let the zero forcing process go. And we're stuck. Again, and we're in that special case that we're stuck because we're not adjacent with any of the leaves, the blue colored leaves. So what we can do is we know that since it's not adjacent to leaves, we can include that in an independent set and just color one of the neighbors and then allow the zero forcing process to continue. So we do this until we arrive at a point where we can't go any further. And the reason is that we have a blue colored vertex that's adjacent with two blue leaves. So we just uncolor one of those and then color a neighbor over there to allow it to go in. And do the same thing over here. And so then that'll force there, and that'll force there. Uncolor this one, color that one, and that will force there, and then it can force over here. Okay, so now all of the vertices from T1 have been colored blue. So notice though, that since at least one leaf neighbor of T2 is adjacent with all the vertices in T1, that now that leaf neighbor can force. And when that leaf neighbor forces, it adds to T2 in a +1 manner, just like we had to add +1 over here to get the zero forcing started on T1. So now what case are we in? Well, this is colored and there's two leaf neighbors that are colored. So we uncolor one and color a neighbor outside of it blue, allowing it to force in, and then there. So this set of colored vertices is a zero forcing set of the graph. And again, it satisfies that the cardinality of that set is equal to the cardinality of the red circle vertices +1. Okay. So let's maybe do a more exotic example. Okay, so drag some. This will be the last example that we do. Okay, so maybe let's say all right, so we have this connected cubic graph. It's not K4. So let's begin by finding our maximum tree, T1. Let's see if I can find it. And then notice that everything outside of it is a P2 component or an isolated vertex. So what we can do is color the leaves of T1. So there is only one maximum degree tree in our forest decomposition. So we're going to color those. And observe that that is also an independent set in the graph. So if there is an isolated vertex adjacent with any leaf, we color that one first, and that'll give us our +1. So +1. And then we let the zero forcing process start. Well, there are no forces available, but we know that this vertex did not force because it's not adjacent with any, it's only adjacent with at most one leaf. So there is some other vertex that's independent from it, independent from the set of leaves. So we're going to include that vertex in our independent set, and then color a neighbor of this one to get it going. So that'll force that to become colored. And then we let the zero forcing process propagate throughout the graph. Okay, so notice that we're stuck. This colored vertex and that colored vertex, they have two white neighbors. So we know that, so if this one was forced by something that was in our independent set, and it has two white neighbors, throughout this whole process behind the scenes, I've been ensuring that it's important that each vertex in I is always blue. Okay. So since I know that this has two non-blue neighbors, at least one of those, even if it was forced by something that was in the independent set here, at least one of these is independent currently. So what I can do is I can include that one in the independent set, color it, and then allow the forcing process to go. And then here, we have that this vertex is adjacent with a support vertex of our tree, and it has one that's not currently in our independent set. So under that property, this neighbor of this vertex that's independent from the blue colored vertices in the independent set and is also not a support vertex, we simply include that in our zero forcing set and then color it. And now this can go here, or if we can choose this to be colored here, and then we have a one-to-one correspondence between that and that. So then there. We're also stuck here. It has two non-support vertex neighbors that are also not colored blue. So we know that they're independent from the current set of independent vertices. So we can just include one of those. Or include this one, actually. I think I prefer to always include inside the tree. That's something that I'm figuring out right now, is to include when you have a choice between out and in from the tree, choose the independent vertex to be in, and then color that one, and let it force out. Okay. We're stuck here as well. It has a neighbor that's independent from the set, so we can include that neighbor inside the tree, and then color there, force it out. And now we're stuck, but we're stuck because we have a newly colored vertex that's adjacent with two leaves, so it would be strong support vertices. So then we just do a swap and allow the vertex to go in there, do a swap, allow, close up, that. So this set of blue colored vertices is a zero forcing set, and it satisfies the property that the cardinality of that set is equal to the cardinality of the set of red circle vertices plus 1. And that is the general idea behind the algorithm. That you can always find this decomposition such that you color all the leaves of the maximum degree trees in this forest, then you can get the zero forcing process started by adding one additional vertex outside of that set of leaves. And then at each time that you stop, you update your set of blue colored vertices and your independent set according to a series of, I think, about 4 update rules. Okay, so hopefully that gives you an idea of what the proof would look like, which, by the way, for those of you that aren't familiar, since that's a zero forcing set, that's at least a zero forcing number. And since that's an independent set, that's at most the independent set plus 1. So if this algorithm is written correctly, I believe that it implies that this conjecture is true. Right. Thank you for watching, and I hope that illuminates it a little bit.